One of the most significant questions regarding polygonal construction technology is what tools and techniques were employed in the stoneworking process. At the same time, the following points need to be considered. The materials used to create polygonal structures could have varying degrees of hardness. Not only individual blocks were processed, but also the rock outcrops, where configurations were created. The only reference point available here is the traces left on the blocks and rock faces. And the first question that arises in this regard is, which of these traces are the result of natural processes, and which are the result of using artificial tools? Of course, it's important not to overlook the fact that polygonal structures and the numerous types of configurations are a permanent imprint, set in stone, of the methods that were used to process the stone. In other words, the question is broader than just the traces of tools. It is a question of the traces of a specific technology being applied. A technology that continues to puzzle many researchers to this day. What can be considered as such traces? Usually, for research, separate areas with clear signs of artificial influence are selected, where the analogy with the results of processing using methods familiar to us is obvious. Then, a series of analogies is mechanically extended, and the traces are compared with known tools today: saws, angle grinders, chisels. But each block of polygonal masonry, for example, has been processed on all its connection surfaces. In the overwhelming majority of cases, the face parts and edges are processed. Artificial shape has also been applied to the backsides. Yet here we no longer find traces that could be compared with those left by our tools. This is a strange circumstance. And it suggests that a significant portion of the traces, which undoubtedly exist, we simply cannot identify as such. This raises an epistemological question. How can we study what we cannot even distinguish or define? This concerns not only tools and methods, but also the polygonal complexes themselves, and their individual components. The same question applies to other artifacts. Tiwanaku, the Nazca lines, pyramids. The development of scientific thought has always been based on the study of reproducible phenomena, whether in astronomy or the animal world. These phenomena are often cyclical. Solar and lunar eclipses, the change of day and night and seasons, tides and ebb, precipitation and lightning, volcanic eruptions and earthquakes, freezing and boiling of water, melting, refraction of light. Observation and experimentation allowed knowledge to gradually expand. Understanding of processes deepened over time. But in the case of polygonal technology, all we have are finished artificial objects. And in them, we can only identify certain patterns and repetitions visible to us. We have no data that would allow us to trace the genesis of this technology. We cannot even reproduce the process itself. The experiments conducted each time reveal the necessity for tools and methods that are entirely unknown to us. This concerns the preparation and placement of polygonal blocks and megaliths, often in hard-to-reach locations. It also concerns their transportation. And here, we can confidently say that the traces shown above cannot be classified as regular. They only testify that stone could have been processed in such a manner as well. But to claim that the masonry was created using these methods is no longer possible, because such traces are not found in the masonry itself. The supposed traces of tools should be divided into several categories. The first category should include striking cases, but at the same time, sufficiently rare. Their rarity may indicate that the tools and methods that left such traces were not used on a constant basis. They are more of an accompanying feature, pointing to potential capabilities. The second category consists of traces that are found everywhere and regularly. But they are not so easily understood, and sometimes not understood at all: grooves, nipples, indentations, edges. It's not always possible to find analogies among what we know and are familiar with. The third category includes phenomena that have been insufficiently studied or not studied at all. Vitrification, magnetic anomalies, cellular structure of limestone surfaces, recrystallization. Systematic research on these phenomena has not been conducted. There are only numerous fragmentary mentions and amateur observations. But on this basis, it is impossible to draw definite conclusions about their nature. It is not even possible to answer the question of what they represent. Are they purely natural phenomena? The result of natural processes in artificially produced material or on artificially prepared surfaces? Or are they the consequence of a biased approach by researchers? It should also be noted that the traces in the first category change from region to region. For example, disc sawing, in Egypt, as well as tubular drilling, are not found in the same form in Peru. And conversely, traces such as melting on one of the blocks in the Sacsayhuaman masonry and on a figure depicting a puma are not found in Egypt. At the same time, traces belonging to the second category, with no significant changes, are found in different regions. Nipples, in Egypt and Peru, in India, Cambodia, and the Caucasus. Grooves, in Aswan, Chachakata, on pyramid cladding, in Sacsayhuaman. Such invariance is direct evidence of the identity of the principles of rock manipulation. And the traces belonging to the first category are a particular example of more specific usage, a kind of boundary case, an extreme task. Many traces on the rock that belong to the first category can be associated with traces left by our tools. For example, an extended groove with a width of up to 1 centimeter. This trace resembles a cut made by a modern tool, especially when there are scratches on the side surfaces. In this case, the groove has a rounded edge, creating an analogy with the trace of a disc saw. Such traces are rarely found in Peru, and they do not have small side grooves. Similar traces can be found on the basalt floor at the base of the Great Pyramid of Giza in Egypt. They do indeed resemble the traces left by our angle grinders. And on this basis, they have been interpreted as traces from an ancient angle grinder. However, a brief look into the past reveals that various construction activities have repeatedly taken place around this object. The floor has been relaid. An electric cable has been run through it. An asphalt road has passed over it. Therefore, it is quite possible that the mentioned traces are actually the result of modern activity. At the very least, we would need absolutely reliable data to argue for their ancient origin. Similar traces can also be found in Turkey. It is clear that this method of processing was used only in certain cases. For example, in Peru, a border is sometimes applied around niches. But it is unlikely that such a method would have been used in the creation of polygonal masonry. The next category of recognizable traces is what are known as drilling marks. In Egypt, we encounter rounded cylindrical indentations resembling traces from tubular drilling. Circular grooves are clearly visible on their walls. The holes found in Peru are made quite differently. Their diameter is inconsistent. There are no grooves. Thus, there is no analogy with drilling. There is also a fairly substantial category of traces that suggest work was done on a material that could deform without subsequent destruction. Many interpret these as the result of working with a pliable material, based solely on visual similarity. In Peru, such traces are most commonly found not in masonry but near configurations. However, characteristic traces of limestone melting are also observed in so-called stone pipes of natural origin. This phenomenon is explained as a result of an explosive process. Therefore, plastic-type traces must be analyzed with the possibility of natural origins in mind and related to the causes that could account for them. This category includes traces that do not have direct analogies with traces left by tools known to us or have certain characteristics for which we have no equivalent. Such traces include extended grooves. Most often, they have a rounded cross-section, but there are also traces with a cross-section close to rectangular. Visually, they resemble regular grooves. The most characteristic features of those found in Peru are parallel edges and uniform depth. When moving from one block to another, the width is often inconsistent. Some grooves appear to be smudged longitudinally, with a distinct outline at one end. On the blocks, these grooves are mostly arranged in pairs, which gives the impression that the pairs are somehow coordinated. However, single grooves are also found. There are also blocks that are true record holders, with up to 10 indentations distributed across the entire surface. In Egypt, these grooves appear to be more standardized. In addition to the Aswan quarries, they are found on granite blocks in the cladding of the Pyramid of Menkora. Often, there is no actual groove, but only isolated elevations or ridges on the surface, indicating that material was removed in those areas. Indentations are regularly found on the face sides of blocks, typically in the shape of a semi-oval or half-rectangle with rounded corners. Most often, they are located in the lower parts of the blocks. Their location on the face side varies. They may be positioned at the center of the block or closer to one of its sides. On some blocks in Sacsayhuaman, they are not found on the front face but almost underneath it. The number of these indentations can range from 2 to 6. When there are many, some of them deviate from the general horizontal level. No correlation between their shape, depth, size, and the mass or dimensions of the block can be observed. These indentations are interpreted as supports used during the installation and fitting of the blocks. However, they are also seen in places where supports would not have been necessary, on blocks from lower layers of masonry, on blocks placed directly on a rock foundation, or on pyramid cladding. The excessive number of these indentations in some cases raises questions about their true purpose. For holding a block, a few of them would suffice. Holding a small block with 6 supports seems highly impractical. Moreover, these indentations are not only found on megaliths and large blocks. They are also present on blocks so small that there could have been no need for supports. And despite this, the size and shape of the indentations appear to be standardized. Grooves and indentations have something in common. If we isolate a short section from the beginning or end of a groove, we get an indentation of the described type. This suggests that such traces are the product of the same impact on the stone that created the grooves. It is simply a more specialized form, serving a specific purpose and corresponding to its location. Moreover, extended grooves are sometimes made in a sequence of smaller indentations, as seen in Aswan or Sacsayhuaman. One more nuance should be noted regarding such traces. The quantity and variety of indentations in Sacsayhuaman are not found in other polygonal complexes. But even there, they are not ubiquitous. The most numerous ones are on the blocks of the first level of the zigzags. Above, despite the similar-sized blocks, these indentations are nearly absent. This may point to technological aspects related to the creation of the face sides of the masonry. It is important to note that while rectangular indentations and grooves resemble each other, they also have many specific features. They cannot be attributed to mechanical standards, such as a bucket or a fantastical laser beam. Among the theories explaining their origin through the pounding method, one suggests that such indentations were created by simultaneous tapping of the surface with two small hammers. However, this raises the question: why are the backs of the grooves and indentations so straight and perpendicular to the sides? To achieve this manually, it would have required deliberate effort. Why, in the case of closely spaced grooves, was there a preserving ridge between them? If we assume the ridge as the result of intentional creation, such a procedure would have demanded care and remarkable skill in stoneworking. Therefore, it makes more sense to view the ridge between the grooves as a side effect of material removal, unrelated to manual processing, that allowed the material to remain intact. This category also includes protrusions that have a nipple-like shape. They are always located on the processed surface, which makes them a result of purposeful activity, a technological trace. However, unlike the grooves, which result from creating seating places, removing material, or detaching stone from the mass, the situation here is the opposite. The excess material has been left behind. Similar protrusions are formed when working with stone in our time. They may be the remnants of lifting tools connecting the base and the detached block. Rigging devices. Markers for the previous surface level to assess removed material volumes. However, this only remotely resembles the protrusions we are concerned with on the surfaces of the blocks. The same difficulty arises when considering the indentations beneath them. Several types of these protrusions can be clearly distinguished. Bosses, large protrusions, which in the final stages were often given a specific geometric shape. Nipple-like protrusions, a fairly characteristic type of protrusion found on the lower parts of blocks. Small hemispherical protrusions on rocky foundations and uncertain configurations, which are conditionally referred to as nubs. And finally, remnants of material left as a result of interrupted excavation processes. The difference between these varieties is significant, in shape, size, and placement. Based on these differences, we can hypothesize that the causes behind the appearance of such features were varied. It is also possible that they served different purposes, or they are side effects of different, unrelated actions. As shown in the second part of the Traces of Foreign Technologies series, the nipple-like protrusion is not formed all at once. It results from a sequential, multi-directional removal of material in small portions. It is possible that traces such as narrow cuts or grooves were also created by such repeated impacts. The overlap of the same type of impact could lead to different forms of removal. In some cases, it was done in portions, while in others, a continuous surface was formed, like a single pass with consistent intensity. This is one of the major difficulties in analysis. It is impossible to definitively determine how extended material removal was carried out. There is ample evidence that smooth surfaces are the result of consecutive overlapping of the same type of impact. In analysis, it is also important to consider that there are many configurations where no signs of portioned material removal are visible. For example, when analyzing the smoothed granite cladding of the pyramids, it is evident that the removal was done not across the entire plane but in sections. How the level was controlled and maintained remains an open question. There are numerous possible options. However, it is significant that there was the ability to create large surfaces in multiple passes. The use of this technique is best seen not on wall facades, which often were not aligned to a single level, but in the creation of tight joints in megalithic masonry made of rectangular blocks with flat connection surfaces. It was also used in pyramid construction, Here, each row of blocks had to be leveled before the next row was installed. Otherwise, the masonry would only be possible through individual fitting of each block, which is feasible for cladding construction, but not for building multi-row structures made of millions of blocks. Defining the boundaries of the tool's impact area is also a complex task. At first glance, everything should be simple. Each cut has distinct contours in the form of elevations, remnants of untouched material, which define its spatial characteristics. However, in the case of the steps in Peru and Egypt, one can observe a continuous side trace. This may suggest some additional volume of impact that was captured only sporadically, partially, unintentionally, and under specific conditions. It is worth noting that although narrow cuts resembling a sawing could have been made, this technique was not used for forming the block blanks or for creating the seating areas or profiles. This leads to the conclusion that the processing that left the groove trace was preferred. Perhaps this also reflected the usual pragmatism of polygonal masonry, which consistently demonstrates calculation and economy in material use. Furthermore, on the blocks, we see not multiple cuts, but a layer-by-layer removal of material. This means that the tool did not leave scraps. The removed material consisted of fine crumbs. If this is the case, searching for waste seems like a completely unpromising endeavor. The joining surfaces of the blocks also fall into this category of traces. It is noticeable that both processed and unprocessed surfaces on the blocks are equally cavernous. The same can be observed in the grooves. However, cavities cannot be attributed to erosion. The surfaces within the joints are protected from the factors that cause erosion, yet cavities are still observed there. They are also found where the joints were exposed in the recent past. Obviously, sawing with a diamond wire or disc is not suitable for obtaining the side surfaces of the blocks. The joining surfaces are curvilinear. There are no scratches. There is also no incidental polishing associated with the process. Moreover, the roughness often increases as you move further from the edge. The closer to the face of the joint, the smoother the surface. This is also observed in Egypt, on the casing of the Menkora pyramid. One could argue that there was some rough fitting and polishing in the joint areas. But this would be far-fetched. It's been repeatedly mentioned that there are no traces of mechanical impact on the side surfaces of the blocks. Additionally, polishing each joint area, especially in materials like diorite or granite, with the tools available to ancient craftsmen, would be an infeasible and irrational task. Moreover, when polishing an edge, the surface level will inevitably drop, and the joint will become loose. This is exactly what was observed in Prochen's experiments. Therefore, any change in level due to subsequent polishing had to be taken into account. In antiquity, for example, this was taken into account, and thus the central part of the joining sections of columns was recessed, or the joining surfaces were placed at an angle. Yet, the joints, often having significant depth, still have a smooth structure only in close proximity to the edge. This includes horizontal joints, without any inclination, which more likely point to the characteristics of the tool rather than manual labor. The edges of the adjoining blocks also belong to the second category of traces. In most cases, the edge areas have a recognizable appearance. Apparently, this served as the prototype for chamfers, starting from ancient masonry. However, the purpose of chamfers and edges is fundamentally different. The chamfer, as can be read in the works of Schwarz, serves to prevent the block's edge from chipping during installation in the event that fragments of the stone fall onto it. This is a well-known point in the construction industry. But only chamfers cut at an angle or with a step have this quality. For polygonal blocks, the edge forms straight and near right angles, and it does not protect the edges of the blocks in any way. The different uses of the edges in polygonal masonry were discussed in detail in the second part of the Traces of Foreign Technologies series. It is worth noting once again that the edges located at the bottom and top of the blocks are different. This should also be viewed as a technological trace. Particularly noteworthy are the lower edges, formed by removing material from a narrow section of the surface. This indicates the asymmetry of the processes related to or preceding the joining. Considering all regions, it is rare for the edges in free-form masonry to be formed not at the bottom but, conversely, at the top with a slope. Similarly, the edges in the honeycomb masonry are made with slopes. In all cases, joining always required preparation of the edge areas in the form of a strip or slope, corresponding to the joining profile, or through leveling the facade for terraces or block masonry. There are no examples of joining where the facade was left untouched. It is precisely the edges, along with the overall treatment of the face surface, that are largely responsible for the convexity of the front sides of polygonal blocks. This type of convexity is found on many parts of polygonal masonry. Rounded, smoothed forms, as if water-worn, are found not only in large blocks. For example, in the foundation part of the masonry in Cusco, there are sections with small similar blocks. Here, rough stone would have made more sense. It is doubtful that cobblestones of such irregular shapes were intentionally selected. A similar appearance is also found in the basalt floor at the foot of the Khufu pyramid in Egypt. Such shapes of blocks suggest a possible specificity in processing. The surfaces were not made flat, as is usual for us, but convex. And this seems to be a somewhat simplified type of processing. In this case, the convex surface is a byproduct of the process. At the same time, one could cite the rare case when the facades of blocks with bosses are recessed. This stands out from all the other patterns and has no clear comparison. Nonetheless, its uniqueness could very well be the result of the variability in the way surfaces of this type were obtained, possibly even intentionally created for aesthetic purposes centuries later. The exact fitting of the blocks along the entire length of the joint in curved profile configurations also belongs to the category of technological traces. Gaps in the joints are extremely rare, mostly appearing at the block corners. The quality of the fit is uniform along the entire length of the profile. It is obviously easier, especially when done manually, to fit surfaces of limited area. But the creators of polygonal masonry were not concerned by large areas. The length of many joints measures in meters. This can also be attributed to the properties of the tools used to process the stone. The quality of the fit does not depend on the hardness or strength of the rocks used to create the polygonal blocks. This point becomes even clearer when considering the manufacturing of miniature objects, such as spools, discs, and vases. In fact, working with hard stones can even be easier, depending on the approach, than working with fragile ones. Nevertheless, it is clear that the strength characteristics of the material, as well as many other factors, did not deter the creators and did not affect the quality of the items. Thus, several characteristics typical of traces in the second category can be identified. They all share a common execution mechanism. A portion of hard material is removed, creating depressions or projections, or achieving the required configurations of the receiving and mating profiles. Surface processing is synchronously performed to the desired quality. It can result in either a polished or rough surface. By reducing the parameters of the groove, traces similar to the cuts on the platform in Ollantay Tombo can be created, as well as more specific traces, such as those on the Puma figure. In other words, this may refer to calibration. By removing material in a specific sequence and direction, traces that resemble plastic deformation can also be produced. As a result, the differences between traces in the first and second groups may be caused by nuances in the use of the tool, the area of the surface being worked, and possibly the precision and care of the execution. Separate are the traces with scratches. They generate the most analogies with our tools. At the same time, some important technical differences remain in the shadows. The vast majority of drillings and cuts have a characteristic U-shaped cross-section, but sometimes the grooves have a tapering profile, which suggests a different method of their creation. The ends of the grooves on the marked platform in Ollantaytambo do not have the characteristic rounding that occurs when using a disc saw. This also leads to the conclusion that a different tool and method were used. In Ollantaytambo, among the megalithic blocks with grooves for the tie, there is a unique case of a groove with small furrows. However, its cross-section deviates from a circular shape, which means it was not made by drilling. This suggests that the scratches might be a byproduct of additional tools used to create holes and narrow grooves. Tools necessary to achieve a more precise shape. The main action, however, could have had the same nature as in the general case. Thus, the distance between the scratches is not the tool's step as a derivative of strength, but the result of the gradual movement of the mandrel. It should be noted that the material removal was mainly done without any drilling traces, with characteristic rounding of the corners. The radius of rounding could vary widely, up to the formation of a pronounced sharp angle. This can be seen in the configurations in Peru and the sarcophagi in Egypt. At the same time, the sarcophagus in the Pyramid of Cheops has drilling traces, and it stands out both in quality and in the technology of its production, which suggests a different author. The same applies to the unfinished sarcophagus in the Cairo Museum. As we can see, sawing was not used to remove the material, instead, traces in the form of grooves are observed. Attempts to modify the finished product may well have occurred later. Therefore, some traces provoke certain associations. It is quite likely that they could have appeared both due to simple technologies of ancient Egypt and in modern times, as happened with the basalt floor. The third category consists of very specific technological traces. These include vitrification. The surfaces of some blocks and structures are locally covered with a film that has the composition, shine, hardness, and glass-like texture of glaze. When viewed at a certain angle and with adequate lighting, it becomes quite noticeable. This phenomenon has been recorded not only in South America, at Kenko, Ollantaytambo, and Sacsayhuaman. Surfaces with such a coating can also be found on Easter Island. Researchers Jan Peter de Jong and Christopher Jordan took samples in one of the caves near Cusco. Their analysis showed that this film could have been formed at high temperatures by applying a ceramic paste to the surface of limestone. However, many researchers believe that these surfaces acquired their appearance as a result of a unique polishing technique. This may occur when locals and tourists, through touching, bring some areas to a glossy finish. Examples of such polishing do indeed exist, for example, the famous miniature insert in the Cusco masonry. But what about areas that are difficult to access? What about the fact that the film on the stone is clearly visible on the fractures? At the same time, the connection between polishing and the unusual chemical composition of the glazed surface remains unexplored. The phenomenon of vitrification, despite the abundance of such traces and numerous mentions of them, has not been studied to the necessary extent. Another type of trace in this category is magnetic anomalies, demonstrated by the blocks at Pumapunku. This phenomenon is well shown in Brian Forrester's video. Unfortunately, even in this case, the nature of the phenomenon remains unclear. There is insufficient data to draw conclusions. It is unknown whether it is a local phenomenon or applies to many polygonal blocks. The causes that may give rise to this phenomenon have not been studied. It could be the natural magnetization of the rocks. But it could also be an artificial anomaly, a result of specific, both directed and non-directed, impacts. This category of traces also includes those found on the surfaces of processed limestone masses around Cusco and Kenko. Such formations are typical of erosional processes. However, nothing similar is observed on the finished blocks in polygonal masonry. The question remains how the processing of the stone is related to its subsequent cellular erosion. Another type of trace is white dots, which are quite regularly found in large quantities on the faces of polygonal blocks in Sacsayhuaman. Many researchers consider them evidence that the blocks were worked using the pounding method, simply by striking them with stones. They do indeed resemble traces left on a block's surface after being hit by a stone. Here it is revealed that limestone is capable of preserving traces of mechanical damage due to subsequent recrystallization at the point of impact. The limestone of Sacsayhuaman originally has light tones. In most cases, the site of impact becomes indistinguishable on the surface after a while. This occurs due to the so-called tanning and erosion. The majority of blocks in Sacsayhuaman do not bear traces in the form of these dots. However, on some blocks, especially where there are abundant calcite veins, scratches and damage seem to emerge on the surface. The causes by which microcracks in the stone lead to such a phenomenon should be studied by relevant specialists. Here, we only note that the surfaces of limestone blocks in some cases can act as a kind of device that records data about the treatment. Let's examine the dots in more detail. First of all, it should be noted that this phenomenon can have a natural origin. They are observed on untreated surfaces as well. Many cracks are filled with crystalline inclusions, which can present a beautiful sight. Such traces can also be produced as a result of manual processing, tapping the surface with stone or metal tools. Freshly worked blocks, just like polygonal ones, are covered with similar points. But there is a significant difference. Along with the points, there are also long scratches. When working by hand, it is not always possible to strike strictly perpendicular to the surface. In our case, the issue is not even the degree of preparation or skill of the stonecutters. With manual processing, the side walls of the depressions should be covered with long scratches. But here, only points are present. There are no lines at all. Their arrangement also does not correspond to what would be expected if the surface was treated with manual tools. The points are spaced at intervals, sometimes quite large. If the surface of such a block was processed entirely, which is not in question, the damage to its upper layer should have been continuous. The frequency of the points increases in the edge area. This could indicate that the treatment of the facade part of the block and its edges were different. Thus, the points may not be residual traces of an impact on the surface. Let's take another look at what the proposed tool could have done. It should have been capable of creating curvilinear joints. Cables, hydroabrasive methods, or lasers would not be suitable for this. Its working body should have been flexible. At the same time, voids and joints were ignored during the process. They were not affected by the treatment. Here, attention should be paid to the condition of the edges of cavities and voids where surface treatment is present. With manual methods, chipping of the edges would have been inevitable. With the plastic state of the rock, corner deformations and material seepage would have been unavoidable. And this points to certain requirements for the tool. Since there are no deformations of the voids or their boundaries, this indicates that the working body had both the necessary flexibility and a rigid structure. It was also able to strictly maintain the set direction. The described properties most closely correspond to electro-impulse processing. Its model can be imagined as a kind of flexible brush, where alternating high-voltage spark discharges between electrodes lead to the disintegration of quartz-containing rocks. At sufficient power levels, it is capable of destructuring limestones. Depending on the number of electrodes and the direction of movement, such a tool can create grooves with cavities, conical depressions, and saws. It should also be noted that limestone does not melt under normal conditions, i.e., atmospheric pressure and gradual heating, which causes calcium carbonate to decompose into calcium oxide, or simply lime. But melting limestone is possible under high temperatures and pressure. In the discharge channel, temperatures can reach high values, and pressure, due to detonation waves, according to studies, can reach tens of atmospheres. Given temperatures of up to several thousand degrees, this may be enough for local melting of limestone, or at least its destruction. Again, this is just a model. For several reasons, it will not be possible to fully reproduce traces through electro-impulse processing. Nevertheless, it demonstrates the fundamental possibility of limestone treatment with subsequent appearance of white dots based on local effects, which have a non-mechanical but a different nature. In general, traces belonging to the third group are quite unique. Based on their inherent characteristics, it can be assumed that they represent either accompanying or even independent moments in polygonal technology, designed to address certain localized, specialized tasks. Further research on these traces may contribute to a fuller understanding of stone processing principles. In addition to the already described, there is another category of traces. They can largely be associated with manual methods of processing, but some technical aspects of their creation or purpose remain unclear. This category includes the megalithic masonry of Baalbek, the Lunju Caves, the Yan Mountain Quarry, and the quarries and temples of Thailand and Cambodia. In each of these cases, there are no traces typical of polygonal technology, such as the absence of manual processing marks, grooves, nubs, or edges. But at the same time, there are unanswered questions. Baalbek, movement of trilithons. Yan Mountain Quarry, carved megaliths. Lunju Caves, enormous underground chambers. Cambodia, temples with precisely fitted blocks. There are also analogies in terms of smaller traces, which resemble the result of using a Trojan tool on the chamfers of trilithons, columns, blocks at Baalbek, and the masonry of the Temple Mount in Israel. Clearly, these traces cannot be attributed to any distinct category. Therefore, they represent a separate type of traces, not related to polygonal masonry and complexes. When examining the described traces, it becomes clear that the main marker of polygonal technology is not the so-called saw marks. They attract attention only because they resemble traces left by our tools. This gives a false impression that they can be analyzed and assessed by the same parameters used for tool-made marks. When analyzing polygonal masonry and structures, the primary focus should be on the edges, curvilinear joints, nubs, and ribs of the blocks. The characteristic features of polygonal technology should also include additional elements, such as the absence of signs of rock splitting with wedges, and the construction of masonry in hard-to-reach places, since this indicates the size of the tools used and their capabilities. This also includes the preparation of seating for inserts, since this required effort to create edges, complementary, and receiving profiles. Additionally, the joints must have been made while simultaneously removing debris and dust from the connection zone, because even small fragments of material can prevent a tight connection between solid blocks. Also, elements such as dry masonry, puzzle masonry, and the creation of the lower portion of ceiling openings through selection, etc., all represent regularities that were noted in the second series of the Traces of Foreign Technologies cycle. Based on these features, it is easy to distinguish the object of study from what might resemble polygonal masonry but is not. It should also be noted that, besides the well-known analogy between polygonal masonry and cellular structures, traces of stone processing resemble the texture of sand dunes, clouds, or thawing snow. These are formed as a single object based on principles described by chaos theory. In this case, the scale of the phenomenon governed by fractal laws, the material structure, and the turbulent flow of the medium, which governs the formation of similar structures, are more important than the material itself. Without taking this into account, one could highlight individual areas, discuss the sequence of material selection and its boundaries, but that would be fundamentally wrong. Our tools mostly use the principle of repeatedly performing the same action with rigidly set parameters of simple geometry. In stone processing, mechanical action is most often required, such as discrete or continuous rotational and reciprocating motion. Discs, saws, chisels, hydroabrasives. And also thermal treatment. But perhaps it is naive to assume that the spectrum of available actions ends here. Nature demonstrates other approaches that we have not yet fully studied. To some extent, this also touches upon the question of the origin of the Nazca lines. If the stripes and figures on the plateau are the result of some kind of effect on the surface with a highly complex configuration, then the technology used to create them could have been based on principles similar to those applied in polygonal construction.